students, welcome to a new session on the chapter Haloalkanes and Haloarenes. In the previous two sessions, we have seen preparation of haloalkanes from hydrocarbons. First we have seen from alkanes, then we have seen the preparation from alkanes. Today we are going to see the preparation of haloalkanes from alcohols. Now, if you study preparation of haloalkanes from alcohols here perfectly, in the next chapter when we will be doing alcohols, phenols and ethers, all this will come under preparation of, properties of alcohol. So, the preparation of haloalkanes from alcohols here will be the properties of alcohols in the next chapter. So this is a major advantage of organic chemistry, that if you study one chapter perfectly, the first chapter perfectly, many of the concepts will be repeated in the second chapter of organic chemistry, and if you study first and second chapters perfectly, those concepts will be useful in the third chapter. So it's it is like kind of advantage, like you can most of the concepts repeat. So try to understand them and learn them perfectly so that you get a proper grip of organic chemistry across the chapter. So now when we see the preparation of haloalkanes from alcohols, we have various reagents using which we can prepare haloalkanes from alcohols. Now in this, the first method is by using concentrated HCl plus anhydrous ZnCl₂. Anhydrous ZnCl₂. This is one method of preparation of alcohols. And you get what? Haloalkanes. And this preparation method is very famously called as Gru's process. This method is very famously called as Gru's process. Now the second reagent, this is one method of preparation of haloalkanes from alcohols. Now the other method is you can prepare by using PCl5, phosphorus pentachloride. Now one more reagent we can use, which is a PCl3. You can prepare haloalkanes from alcohols even by using PCl3. And the last but not least, in fact the most important preparation method, and the most preferred preparation method of haloalkanes from alcohols, because the yield is very good and very advantageous. Why and all those things we'll see when we are doing it with SOCl2. And this is called as your Dalton's reaction. This is your Dalton's reaction. So two named reactions are there in this, and all the reactions are very important. So we can prepare haloalkanes from alcohols by using four reagents. The first reaction will be reaction of alcohols with with concentrated HCl plus anhydrous ZnCl₂ to give haloalkanes, and this process is called Gru's process. And the second reagent we can use for the preparation of haloalkanes from alcohols is PCl5, and then we can also use PCl3, phosphorus trichloride, to prepare haloalkanes from alcohols. And the last and the most important and the most beneficial method for the preparation of haloalkanes from alcohols is SOCl2. SOCl2 is your thionyl chloride, and this is your Dalton's reaction. Today we are going to see in detail about the Gru's process. It is a very important process. We will see the mechanism of Gru's process. Which alkyl halides preferably give Gru's process. What is the intermediate? What is the role of intermediate in deciding the yield of the reaction? And we will also see Lucas test. So let us do the first preparation method in this, where we prepare haloalkanes. We prepare haloalkanes by using the reagent. So I will name this as A here. A, B, C, D. We will do it in continuation. From alcohols I can prepare by using concentrated HCl plus anhydrous ZnCl₂. This is my reagent. What do you call this reagent? I will tell you, giving your alkyl halides plus H2O. Here I didn't write the byproducts because for every reaction here the byproducts are different. So from alcohols I can prepare my haloalkanes by using concentrated HCl plus anhydrous ZnCl₂. Now very important point here, concentrated HCl plus anhydrous ZnCl₂, we call it as Lucas reagent. What do we call it as? We call it as Lucas reagent. Very important. What is Lucas reagent? Lucas reagent is concentrated HCl plus anhydrous ZnCl₂. Now when you see the reagent, concentrated HCl, the use of concentrated HCl is very much understood, because to prepare alloalkanes from alcohols, you need Cl. Okay, you need OH to be substituted by Cl. That is the reason we are using concentrated HCl. That is very much understood. Now, why are we using N-hydrous ZnCl₂ is a very important thing for us here. Now, when we write the importance of N-hydrous ZnCl₂, N-hydrous ZnCl₂ is a Lewis acid. Okay, N-hydrous ZnCl₂ is a Lewis acid. Now, if you go back to your grade 11 in ionic equilibrium chapter, you people have studied what are Lewis acids and Lewis bases. Lewis bases, okay, they donate the electrons because they have lone pair of electrons, whereas Lewis acids, okay, they do accept electrons. Okay, Lewis bases will donate the lone pair of electrons and Lewis acids will accept the lone pair of electrons. What do Lewis acids do? They accept lone pair of electrons. So here, what is the advantage of having N-hydrous ZnCl₂ along with concentrated H2SO4? It weakens RO bond. Okay, it weakens RO bond. Clear? So in alcohols you have ROH, so you have RO bond. The carbon oxygen bond. So anhydrous ZnCl₂, okay, being a Lewis acid, will weaken the RO bond. So when this bond gets weakened, it is very easy for my Cl to substitute OH. That is the reason we use anhydrous ZnCl₂. So in a way we can say it is used as a catalyst. Okay, in a way we can say it is used as catalyst because when RO bond gets weakened, the rate of the reaction obviously increases, so it is actually used as a catalyst in this reaction. So concentrated HCl plus anhydrous ZnCl₂ together is called as Lucas reagent, and I told you the importance of anhydrous ZnCl₂ in this reaction. Now when we go further about this reaction, it is an SN1 type of reaction. Okay, it is SN1 type of reaction. Now you people know what is SN1. It is nucleophilic substitution type 1 reaction. Why and all we will see when I show you the mechanism. I'll tell you why it is SN1 type of reaction. Why it is SN1 type of reaction. Now one more thing if we want to understand here is, okay, now when we talk about the reactivity of various alkyl halides, reactivity of various alkyl halides towards SN1 type of reaction, nucleophilic substitution reaction is basically what? Okay, now here OH minus is a nucleophile. Nucleophile is what? Nucleus loving species. Okay, OH is a nucleophile. Okay, OH is a nucleophile. Clear? Nucleophile always need not be a negatively charged species. Any species which has lone pair of electrons is also considered to be nucleophile. Clear? Nucleophile can be a species which have negative charge on it, or nucleophile can also be a species which has lone pair of electrons on it. Now here if you see this nucleophile, okay, this nucleophile is substituted by one more nucleophile, which is what? Your Cl. Okay, is substituted by one more nucleophile, which is your Cl. Now when one nucleophile is substituted by other nucleophile, we call it as what? We call it as nucleophilic substitution reaction. When one nucleophile is substituted by other nucleophile, we call it as nucleophilic substitution reaction. We'll see this in very much detail when we are doing properties of haloalkanes. In so much detail we'll do it, but how much you need to understand for this particular reaction, I am telling you that much. So here one nucleophile will be substituted by other nucleophile which comes from concentrated HCl. Okay, which comes from concentrated HCl, forming RCl plus H2O. Here I can directly write RCl because I am dealing with concentrated HCl plus anhydrous ZnCl₂. Now when we talk about SN1 type of reaction, or when we are talking about nucleophilic substitution reaction and the reactivity of various hydrogen halides, okay, Hi, then my HBr, then comes my HCl, and then comes my HF. Okay, and then comes my HF. Okay, the most reactive hydrogen halides are hydrogen iodide, then HBr, then HCl, okay, then HF. If we talk about the reason, HI is more acidic. HI is more acidic. Why it is more acidic? It gives H plus easily. Okay, it gives H plus easily. Now when it is more acidic and when it gives H plus easily, what happens? I minus is formed Okay, I minus is formed easily. Okay, I minus is formed easily, and I minus is the better nucleophile. I minus is a better nucleophile compared to your Cl minus, okay, Br minus, Cl minus and F minus. As I minus is a better nucleophile compared to B minus, Cl minus and F minus, Hi will preferably show more rate of reaction towards nucleophilic substitution reactions. This we'll see in detail further, but for now, if you get any question about the reactivity of hydrogen halides towards the nucleophilic substitution reaction, so this is how you should, okay, this much you need to know and remember. So okay, till now what did I tell you? We have four reagents to prepare haloalkanes from alcohols, and I made you know the four reagents. Then I told first we'll be preparing haloalkanes from alcohols using a Lucas reagent, concentrated HCl plus anhydrous ZnCl₂, and I also told you the role of anhydrous ZnCl₂. It's a Lewis acid. It can accept a lone pair of electrons. It weakens the RO bond, and OH is a nucleophile which is substituted by the nucleophile which is coming from concentrated HCl. That is the reason we call this reaction as nucleophilic substitution reaction. Okay, and I told you it is an SN1 type of reaction. No, if you want to understand in a better way why it is an SN1 type of reaction, we need to understand, okay, we need to understand what? We need to understand the mechanism of which process is this called as Gru's process. Okay, what is this process called as Gru's process? What is Gru's process? The production of haloalkanes from alcohols by using Lucas reagent is called Gru's process. Now let us see in detail the mechanism of this reaction, then we will see few examples to understand it in a better way. Now let us see the mechanism of Gru's process. Okay, let me take alcohol first. And you people know oxygen has two lone pair of electrons here, two lone pairs of electrons here. So it is electron rich. That is the reason it is a nucleophile. Now plus ZnCl₂. I already told you ZnCl₂ is a Lewis acid, so it wants electrons, so it will prefer to take electrons. Now when ZnCl₂ sees an oxygen which has two lone pair of electrons, ZnCl₂ will try to take the lone pair of electrons from oxygen. Oxygen being electron rich would want to give the electrons, so ZnCl₂ is in need of electrons as a Lewis acid, so it takes the electrons from oxygen. Now what do you get here? RO, because oxygen has given a lone pair of electrons, it has positive charge and it has its other lone pair of electrons. Okay, now I'll write hydrogen down for the convenience. Okay, and I'll write this lone. If you don't write this lone pair also, it's fine. But because you need to understand there is a lone pair, I'm just writing it. Okay, now here ZnCl₂ will come and get attached to oxygen because it will form a bond with oxygen by taking its lone pair of electrons. So ZnCl₂ will get a negative charge here. So hope the first step is clear for you people. Oxygen being electron rich and ZnCl₂ being electron deficient, and because it's a Lewis acid, it takes the lone pair of electrons from oxygen. As oxygen gives lone pair of electrons, it will get a positive charge. Okay, and Zn, because it is taking lone pair of electrons, it will get a negative charge. Now if you see here, okay, what will happen is this reaction proceeds to the formation of a carbocation. Now what will happen, you people know oxygen is not stable with its positive charge because oxygen is a electronegative atom. Oxygen is an electronegative atom. It would never want to be there with a positive charge. Because oxygen doesn't want to be there with a positive charge, it will pull this lone pair of electrons towards itself. What it will do? It will try to pull the lone pair of electrons towards itself. Now when oxygen is trying to pull the lone pair of electrons towards itself, what will happen? What will form here? R plus will form because the alkyl group has lost its electrons, has lost its state pair of electrons to oxygen. It will get a positive charge. Oxygen will not get a negative charge. It will become neutral because previously it had positive charge. Now it has taken this pair of electrons, so oxygen will remain neutral. So this will get separated as R plus because it has lost its state pair of electrons. So this will become a carbocation. What will happen to this? This will become a carbocation, an electron deficient species. Plus, okay, oxygen will regain its pair of electrons, so oxygen will get a neutral charge. Okay, and here I will have my ZnCl₂. Okay, I'll get R plus carbocation plus OH. Oxygen has got back its lone pair of electrons, so OH ZnCl₂. Now comes into play my concentrated HCl. Okay, because it is an acid, it will give H plus Cl minus ions. Now this carbocation will react with Cl minus from there, and you will get RCl. Okay, and you will get RCl. So one nucleophile is getting substituted by other nucleophile. So I can call it as a nucleophilic substitution reaction. You also have H plus from here. So what will I get? This H plus will react with OH, forming H2O, and I have my ZnCl₂. Clear? So I got back my anhydrous ZnCl₂. So you people would have studied in your previous classes, the catalyst will never be consumed in the reaction. At the end of the reaction, you will get back your catalyst. At the end of the reaction, you can retain your catalyst. Okay, what is the byproduct formed here? H2O, ZnCl₂, we use it as a catalyst. Now I told you ZnCl₂ is used to weaken the RO bond. Now it can be justified from the mechanism. Now because ZnCl₂ has come towards alcohol, okay, oxygen has given its lone pair of electrons to ZnCl₂, and oxygen has got a positive charge. Because of ZnCl₂ only oxygen has got a positive charge, so it started pulling electrons from the alkyl group. Okay, that is the reason this R has become carbocation. So who is responsible for the breaking of this RO bond? ZnCl₂, because it has taken electrons from oxygen. Clear? And if you see here, this reaction, the formation of carbocation is the rate determining step, because it is the slow step. Now whichever step is the slow step in the reaction, that is considered to be the rate determining step. The slowest step in any chemical reaction will determine the rate of the reaction. So what is the rate determining step in this reaction? It is the formation of carbocation. Now it is a nucleophilic substitution reaction. Because one nucleophile has been substituted by other nucleophile. It is a nucleophilic substitution reaction. Okay, followed. Okay, we'll write it in a better. It is a nucleophilic substitution reaction. Okay, involving the formation of carbocation. Okay, involving the formation of carbocation in the rate determining step. Okay, now because as it is a nucleophilic substitution reaction involving the formation of carbocation in the rate determining step, this is my SN1 reaction. SN1 reaction always going to pass through the formation of carbocation. SN1 reactions always pass through the formation of carbocation. Now if we talk a very important concept here, now because I little bit will throw a light on the stereochemistry of this reaction. Okay, we'll try to understand the stereochemistry of this reaction. And why do we need to understand the stereochemistry of the reaction? I will tell you, because okay, as such RCl only is formed, but carbocation, if we see the structure of carbocation, I'll just show you the structure of carbocation. Here for some time I am imagining, okay, the carbocation to be CH3+. For some time I'll imagine the carbocation to be CH3+. It is the intermediate of the reaction. What is the intermediate of the reaction? I'll write that also here. What is the intermediate of the Gross process? Intermediate is your carbocation. Okay, intermediate is your carbocation, and you people know the rate of any reaction will depend on the formation of intermediate only. Now for some time we will see the structure of carbocation to understand the stereochemistry. Now if you see the structure of carbocation, it is a trigonal planar structure. Okay, it is a trigonal planar structure. So a trigonal planar structure because everything is on the same plane. Okay, all the atoms will be on the same plane, and the structure is here trigonal planar structure. Trigonal planar structure, because the hybridization is what here? carbon is sp2 hybridized. Carbon is sp2 hybridized. Okay, carbocations show which type of structure? Trigonal planar structure, where carbon is sp2 hybridized, so it is your trigonal planar structure. Now this is my intermediate, carbocation is my intermediate. Now because it is a planar structure, okay, there are two possibilities for the attack of the incoming nucleophile. Now nucleophile is approaching the carbocation. There are two possibilities of attack of your nucleophile. It can attack from the back side. Now Cl minus is my nucleophile here. Cl minus can attack from the back side, and Cl minus can also attack from the front side. Okay, Cl minus can attack from the back side, and Cl minus can also attack from the front side. So now when the attack is from the back side, you will get an inverted product. If the attack is from the front side, you will get a retention product. Okay, now what is retention product, what is the inversion product? I'll make you understand by taking an example. Okay, okay, before that I'll tell you something. If I have taken an alcohol, right? If the alcohol's configuration is D, small d, you have studied this in your grade 11 when you are studying stereochemistry, dextro and levorotatory. Okay, dextro and levorotatory. The stereoisomer which rotates the plane polarized light towards right side, I call it dextrorotatory. The stereoisomer which rotates the plane polarized light towards the left side, that is levorotatory. So we classify a compound, a chiral compound, into dextrorotatory or levorotatory based on their capability to rotate the plane polarized light. Now, okay, so when I talk about if alcohol is dextrorotatory, now I have done the reaction using Lucas reagent. Now I will get RCl. Now one RCl will be of D configuration as the substrate, and the other RCl which I am getting here will be of L configuration. So the attack of Cl, if it is from the front side, then the configuration is retained. Okay, because OH will go and Cl will come at the same place. If it is if it is attacking from the front side, so the configuration is retained. Now if the Cl is attacking from the back side, okay, OH will leave from the front side, Cl will attack from the back side. So now the configuration is reversed. This becomes levorotatory. Okay, this becomes levorotatory. If the attack is from the front side, the configuration is retained. If the attack is from the back side, the configuration is reversed. Now what will happen here? There is retention. If you want, I will write like this for your better understanding. Attack from back side. Okay, attack from back side. If the attack is from the front side, the configuration is retained, so it will remain dextrorotatory. If the attack is from the back side, the configuration is inverted, so you will get levorotatory. So this is retention, okay, and this is your inversion. Okay, this is your retention and this is your inversion. Now if you see the mechanism of SN1, okay, they will almost be like retention and inversion will almost be like 50-50%. Now the retention product and the, not exactly 50-50, for now we'll consider it to be 50-50. Okay, now this retention product and inversion product together, we call it as racemic mixture. Okay, we call it as racemic mixture. Clear? Okay. So when carbocation has been attacked by nucleophile, there are two types of attacks. One is from the front side, one is from the back side. When the attack is from the front side, I get a retention product. When the attack is from the back side, I get an inversion product. And in retention product plus inversion product together will form racemic mixture, and racemic mixture is optically inactive. Individually, okay, the retention product is optically active because it is rotating plane polarized light towards right side, and individually the inversion product is also optically active because it is rotating the plane polarized light towards the left side. But together when you combine it, okay, the plus configuration will be cancelled out by the minus configuration, because D usually you take it as plus, L usually you take it as minus. So they were like equal and opposite. So when they combine, the plus will, okay, the plus and minus combine, all together you get a neutral thing. Okay, so how much of the rotation is happening to the right side, that much rotation will happen by this compound towards the left side. So together, okay, this rotation has been cancelled by this rotation, and ultimately when the racemic mixture is formed, the racemic mixture will be optically inactive. Clear? So this is about the stereochemistry of the reaction. So whatever haloalkane you are getting, you will get in haloalkane with two configurations. One is the retention configuration and other is the inversion configuration. Now if I just take R and if I teach you, you will never understand the concept that properly. Okay, I have just shown you what is the intermediate. Because the intermediate is carbocation, the attack can be from the front side, the attack can be from the back side. Now to understand, so you people have understood the mechanism, what happened here. Okay, attack happened, later carbocation has formed, it has taken Cl minus from concentrated HCl and H plus from here. I retained my catalyst, I got my RCl plus H2O. Okay, I got my RCl plus H2O. Now to understand the stereochemistry better, let me take an alcohol. Let me take an alcohol which has a chiral center. Okay, which has a chiral center. Now you people know, if any compound has to show optical activity, if any compound has to show optical activity, it has to be it should have a chiral carbon. So let us take a very proper example. This generally I have taken ROH, any alcohol, but to understand the stereochemistry better, let us take a chiral the alcohol containing chiral carbon, so that I can make you understand this retention and inversion in a very better way. So let us see that now. Now let us take an alcohol to understand the stereochemistry part better. Okay. Now let me take an alcohol. Okay. Now this is my alcohol. Okay. If you see, I have taken I have taken an alcohol. If you observe this alcohol, I have a chiral carbon. Okay, I have a chiral carbon. I have a chiral center here. I have a chiral center. Okay, what is chiral center? What is chiral center? I'll give a quick recap. Carbon, okay, carbon attached to 4 different groups. Okay, carbon attached to 4 different groups. Then I call it as chiral carbon. Now if you see here, carbon is attached to 4 different groups. One side it is attached to ethyl group, other side it is attached to methyl group, then one side with OH group, and the other group is hydrogen. Now this is a chiral center. Okay, this is a chiral compound. Now you people know chiral compounds are optically active. Chiral compounds are what? They are optically active. Chiral compounds are optically active. Now you can understand stereochemistry in a very better way if I take a chiral compound. Now here what should I take? I will take my Lucas reagent, concentrated HCl plus anhydrous ZnCl₂. Now from here, what is the nucleophile? What is the nucleophile I'll get from this reagent? Cl minus is my nucleophile. Okay, now the nucleophile I told you very clearly. Now I will, okay, there is a carbocation. The carbocation is planar, and the attack can be from either front side or back side. Or let me write one more step here. Okay, so here what will happen? Anhydrous ZnCl₂ will attack. Anhydrous ZnCl₂ will attack, and I'll get my carbocation. So I will directly write the carbocation here. So what will be the carbocation produced here? Okay, what will be the carbocation produced here? You people know OH will be going with ZnCl₂, forming ZnCl₂OH. So my carbocation will be C2H5, okay, CH3H. Okay, plus you people know this OH will be attacked by anhydrous ZnCl₂, and you know what is the other thing which is produced here? Anhydrous Zn. Okay, it will be your ZnCl₂ plus H2. These are the byproducts. We are not much bothered about the byproducts, because the product RCl stereochemistry is decided by carbocation, is decided by this carbocation. Okay, what is this now? Okay, I'll erase it because you people know the byproducts here. Here we are doing this only to understand stereochemistry. Now this is my carbocation intermediate. Okay, this is my carbocation intermediate. Now you observe. Okay, now Cl minus will come from concentrated HCl. Okay, now this Cl minus can attack from the front side. Okay, front attack. Now this Cl minus can attack from the back side. Cl minus can attack from the back side, so it is your back attack. Okay, now if the attack is from the front side, okay, now I'll get two products here. Now I'll get two products here if the attack is from the front side. Okay, if the attack is from the front side. Now when the attack is from the front side, now see here, when the attack is from the front side, your Cl will come here. Okay, your Cl will come here, and I will write the remaining groups here, C2H5, okay, CH3H. Okay, now see when the attack is from the back side. Okay, now when the attack is from the back side, what will the product that is formed here? C2H5. Now because the attack is from the back side, Cl will be here, CH3 will be here, and H will be here. Now, which one is a retention product and which one is the inversion product? Now if you see, okay, OH is on the right side here. Okay, here OH has replaced Cl has replaced OH from the same side. Okay, Cl has attacked from the front side, so you exactly see Cl at the same position where OH was. You exactly see Cl at the same position where OH was. So this will be my retention product. Okay, and this will be my inversion product. Okay, this will be my retention product and this will be my inversion product, and both together, what do I call it as? And both together I call it as racemic mixture. Okay, if the configuration of this compound is small d, then this will be small d and this will be small l. If the configuration of this is small l, now this will be, okay, this will be small l and this will be small d. So whichever configuration is there here, if it is retained, it is retention, and if it is inverted, because it has attacked from the back side, Cl minus has taken the position opposite to OH minus. Cl minus has taken the position opposite to OH minus. So I call this product as my inversion product. Okay, hopefully by this example your stereochemistry concept is clear. Now one more important concept we will study here. Okay, one more important concept we'll study here. What is that important concept? Is rate of reaction depending on the intermediate. Now we know carbocation is the intermediate. Okay, carbocation is the intermediate. Now which carbocation is more reactive, which carbocation is less reactive? So what am I trying to tell here? Okay, let me tell. Rate of reaction of alcohols, okay, rate of reaction of alcohols in Grove's process. Okay, we have three types of alcohols: tertiary alcohols, primary alcohols, and secondary alcohols. Okay, alcohols are of three types: tertiary, secondary, and primary alcohols. Now when we talk about the reaction of alcohols with Lucas reagent, what is the rate of the reaction of these three types of alcohols towards the Lucas reagent? Now if you see the reaction, tertiary alcohols are more reactive, then comes your secondary alcohols, and then comes your primary alcohol. This is the rate of reaction of your alcohols in Grove process. Tertiary alcohols are more reactive, then comes your secondary alcohols, and then comes your primary alcohols. If we see the reason here, now you people know tertiary alcohols, okay, tertiary alcohols will produce which carbocation? Tertiary carbocation. Okay, will produce tertiary carbocation. Secondary alcohols will produce secondary carbocation. Primary alcohols will produce primary carbocation. Now you people know whichever carbocation is more stable, that reaction is preferred, because tertiary alcohols are giving more stable tertiary carbocation, their rate of reaction is more. And secondary alcohols produce secondary carbocation, which is relatively less stable than tertiary. It will be less reactive, and primary carbocation is the least stable carbocation. That is the reason primary alcohols show very low rate of reaction. Okay, so what is the reason of this reactivity order of alcohols? It is based on the stability of carbocation. What decides the rate of reaction here? Stability of carbocation, which is the intermediate, will decide the rate of the reaction here. And now this difference in the rate of reaction will help us to distinguish tertiary, secondary, and primary alcohols, because three of them don't react in the same way towards the Lucas reagent. Now this difference in the reactivity of alcohols towards the Lucas reagent helps us to distinguish these three types of alcohols. Now how is that happening? How do we distinguish tertiary, secondary, and primary alcohols based on their reactivity towards Lucas reagent? Let us see now under the special side heading, which is your Lucas test. As I told you, tertiary, secondary, and primary alcohols react at a different rate with the Lucas reagent. Okay, now alcohols, when they react with Lucas reagent, they give RCl. Okay, and this RCl is a white PPT. Okay, or you can see, or you can also call it as turbidity. Okay, or you can also call it as turbidity. Now, okay, the white PPT formation will take place when alcohols react with Lucas reagent, because whatever RCl formed, it is a white PPT. Now let us see how do different alcohols react to, okay, react to Lucas reagent. Now if I take a tertiary alcohol, I just now mentioned tertiary alcohols produce tertiary carbocation, which is very much stable. That is the reason the rate of reaction of tertiary alcohols with Lucas reagent is pretty good. So here it will form, okay, it will form RCl. Okay, now let me not write again RCl. Let me keep it very simple. It is understood that RCl is produced. It is understood that RCl is produced. So let me not write again and again. So tertiary alcohols will produce white PPT, and they will produce white PPT immediately. So if you see a white PPT formation immediately, then which type of alcohol it is? Then it is tertiary alcohol. So tertiary alcohol on reaction with Lucas reagent give a white PPT immediately because the rate of reaction is high. Now when we take secondary alcohol, okay, now when we take secondary alcohol and make it react with Lucas reagent, okay, make it react with Lucas reagent. Here also, because secondary carbocation is not that stable as tertiary carbocation, but it is pretty much stable. So it will give white PPT in 5 to 10 minutes. Okay, so if the formation of white PPT is taking time around 5 to 10 minutes, then which type of alcohol it is? Secondary alcohol. Now when I take my primary alcohol, okay, when I take my primary alcohol and react it with Lucas reagent, okay, there is no PPT formation, there is no white PPT, okay, there is no white PPT at room temperature. Okay, at room temperature you don't find any PPT. So primary alcohol, because it produces primary carbocation, which is very much less stable. So when I treat it with Lucas reagent, it will not form any PPT, white PPT at room temperature, because the reaction is not taking place only at room temperature. Now what I will do is, now I will heat it. Now when I heat it, then you can see the formation of white PPT. Okay, when you heat it, you can see the formation of white PPT, but at room temperature, you will not see any white PPT. So for a primary alcohol to react with Lucas reagent, what you should do, it will not normally react. You have to heat it. Okay, you have to heat it. First, the tertiary and secondary alcohol, you need not heat it because they are pretty much reactive with Lucas reagent. So primary alcohol, when they react with Lucas reagent at room temperature, they won't form any PPT, but when you heat it, okay, but when you heat it, they can form a white PPT. So the reaction of primary alcohols with Lucas reagent takes place when you slightly heat it. Now, okay, can I say it like this? Lucas test is used to distinguish, Lucas test is used to distinguish primary, secondary and tertiary alcohols. Okay, Lucas test is used to distinguish primary, secondary and tertiary alcohols. Very important test it is, very important test to distinguish primary, secondary and tertiary alcohols. This will again come in the properties of alcohols when we do alcohols, phenols and ethers. Now let us see a very important question to how to apply Lucas test in the examination when they give MCQs. So that will help you for better understanding of Lucas test questions when they come in the exam, how to answer those questions. Now let us see that question. Let us see this question to understand Lucas test in a much better way. Which of the following gives positive Lucas test? Now you people know, okay, you people know they are not talking about any heating, so we'll take room temperature as a condition. We'll take room temperature as a condition. So tertiary will give Lucas test. Okay, secondary also will give Lucas test. Primary will not give Lucas test at room temperature. So if nothing is given, I'll take it as room temperature. Okay, if nothing is given, I'll take it as room temperature. And a very quick reminder. Okay, rate of reaction is directly proportional to stability of carbocation. Okay, rate of reaction for this is directly proportional to the stability of carbocation. So if the alcohol is producing more stable carbocation, the rate of reaction will obviously be more, and they'll give a positive Lucas test. Let us quickly keep these things in our mind so that we can solve this question properly. which also following gives positive Lucas test. Okay, now if I see here, this is a primary alcohol. Now this is my secondary alcohol. This is carbon is attached to only single carbon, so this is my primary alcohol. Carbon holding OH is attached to 3 carbons, so this is my tertiary alcohol. The carbon holding having OH is attached to 1 carbon, so it is primary. Carbon attached to OH is further attached to 2 carbons, secondary. Carbon which has OH is attached to 1 carbon, primary. Carbon which has OH is attached to 3 carbons, so it is tertiary. We people very well know that this will not give Lucas test because it is primary alcohol. In normal conditions, it will not give Lucas test. Now, if you see here, this is my secondary alcohol, so this will give my Lucas test. Okay, so this is my primary alcohol. Now many children will do this thing only here. Okay, it is a primary alcohol, it will not give Lucas test. This is how you will think. Let me keep this on hold. I'll go to tertiary and come to here. This is a tertiary alcohol, forms a very stable carbocation, so it will give Lucas test. And you people will mark that. Okay, B and D will give Lucas test because they are secondary and tertiary alcohols, whereas 1 to obviously will not give because it is primary alcohol. But C. Now if you see the example C, here children will do a mistake. I agree it is a primary alcohol. But okay, primary alcohol will not give Lucas test, that is there. But beyond that, what is our major criteria to decide the reactivity? Our major criteria to decide the reactivity is stability of carbocation. Now, if you see the carbocation, this alcohol will produce. This alcohol will produce. It will produce this carbocation. Okay, it will produce this carbocation. When OH goes, it will form this carbocation. Now, if you see this carbocation is resonance stabilized. Okay, you can see conjugation here. Positive charge, single bond, double bond. Positive charge, single bond, double bond. So there is a conjugation. So that is the reason this carbocation is resonance stabilized. Now resonance is definitely a very major factor for me here to consider, because rate of reaction will depend on the stability of carbocation. Now if this molecule is producing a resonance stabilized, this is your benzyl carbocation. If you want to know, it is your benzyl carbocation. Here the benzyl carbocation has conjugation, so it will be a resonance stabilizer carbocation. Now in general, if I talk about the carbocation stability here, so tertiary carbocation will be the most stable one. Then comes my benzyl carbocation. Okay, then comes my secondary carbocation, and then comes my primary carbocation. So this is the order of stability of various carbocations. First will be your tertiary carbocation, then it will be your benzyl carbocation, then secondary, and then primary. So primary carbocation being the most stable one will obviously give the Lucas test, but you should not ignore the resonance stabilizer carbocation. Because the carbocation is resonance stabilizer, the reaction rate will be pretty good, giving positive Lucas test. And obviously secondary will give and primary will definitely not give. So be very clear, don't blindly see primary and put the option as it will not give Lucas test. Check which carbon, any question it's better. If you are seeing any benzene ring or something, it's better to check if it is resonance stabilizer and then go for the option. So which molecules will give Lucas test here? Okay, so your answer should be B, C, D. 3 of them will give positive Lucas test. A will not give because it produces primary carbocation. Though C also produces primary carbocation, it is resonance stabilizer resonance stabilizer carbocation. So that will make that will lead to very good rate of reaction, giving a positive Lucas test. So this is a very important question to understand. Okay, how do different alcohols react to the Lucas reagent. So hope you understood this concept. Very important question. Okay, usually children get confused here, so I have taken this question. So in today's session, I have discussed in detail about the Gru's process, which is production of haloalkanes from alcohols using Lucas reagent. I discussed the reaction, I discussed the mechanism, then the stereochemistry, then the rate of reaction of different alcohols towards Lucas reagent, and then I discussed a question for your better understanding. Hope you loved the session. I try to do it in detail. I can wind off this reaction in just 5 to 10 minutes. But you should know the reaction and the stereochemistry to understand a little good level of questions. That is the reason I have put effort, I have put effort with lot of love to make you understand the growth process in a very better way, because questions keep coming even from Lucas test. Okay, hope you understood today's session. Keep watching our channel, keep loving our channel, share it with your friends so that they get the concept in a better way. Okay, till I see you in the next class with the next preparation of haloalkanes from alcohols. This is your Keerthi ma'am. Bye bye.